All right. So to let you guys know what's going on here in terms of our Hawk stuff, if we go over here and log in on our Hawks, over here today, if you haven't done your lessons from 5.1, they are due. Quiz number 9. What I hear, it is not open. There's a date issue on the thing. I'm going to fix it right after class, and I promise you it will be open right out of class, and it will be due, obviously, the quiz is always due on Saturday. This is how Ms. Schaefer has set this thing up here. So they're due on Saturday, and then obviously your 5.2 and 5.3 lessons are actually going to be due on Sunday. We're actually in 5.4, just to let you guys know, but so go ahead and get your 5.4 lessons done as well, because and why not 5.5? So because we got our test coming up pretty soon. So, all right, and let me click over here, and there we go. So last time, and just to give you guys a kind of a indication of what's going on here, let me write down my rules again. These are the rules you need to know. Now, we're in section 5.4, and we kind of finished about halfway through this thing, so we're going to pick it back up. But again, I'm going to keep reiterating these things. So, in 5.3, we did logarithms, and there were 2 forms of logs. There's the basic rules, so this is rules for differentiation. Here are my rules. Rule number 1, if y equals the natural log of x, then y prime is equal to, what's the derivative of natural log of x? 1 over x, things you have memorized. And number 2, then you got the chain rule version of the logarithm. And if y equals the natural log of a function, then y prime is equal to 1 over the function times the derivative of the function. And you can clean that up, but this is the way I want you to memorize it, 1 over the function times the derivative of the function, which ends up becoming the derivative over the actual function there when you clean it up. But these are your 2 logarithm rules. But more important than that was John's fundamental calculus. John's fundamental calculus is very simple. It is better to clean up your algebra before your calculus than afterwards. So when you get a natural log of something that's very convoluted, a lot of multiplication, division, and stuff with powers, use your log properties and first clean them up. Multiplication turns into addition, division turns into subtraction, powers get to go out front. Use your log properties that you're supposed to have memorized from high school, and then take derivative. It'll make it so much easier for you guys. Use your log properties, the beauty of logs. Now, this was in section 5.3. In section 5.4, we're looking at the exponential form. So continuing with the rules, here's rule number 3. If y equals e to the x, that e base 2.781828 ... goes on forever. That natural number e, it shows up in nature naturally. So when we study this stuff, that base e is kind of an important exponential function, that e to the x. And the reason why it's so important is very simply this. What is the derivative of e to the x? E to the x. It's the easiest thing to remember. It's the only function besides 0 in the universe that's its own derivative. So it grows at a rate proportional to itself. It grows at a rate exactly to itself. Derivative of e to the x is e to the x. But then you got the chain rule version of this guy. And the chain rule version says this. If you got y equal to e to a function, then the derivative is going to be e to that function times the derivative of the exponent. That times the inside chain rule stuff. So for each rule, there's a rule and there's a chain rule version. So this is the chain rule version for the log, and this one is the chain rule version for the exponential. Derivative of e to a function is e to the function times the derivative of the exponent. So these are the rules you've got to have memorized. So now we're doing this wonderful application stuff. So pick up where we left off last time, and which was, and we did both of those problems, but number 2 down here. Number 2 states this in terms of our learn mode. Find the first and second derivative of this function here. G of x is equal to negative 6x squared minus 5 e to the x. Well, First derivative, well, derivative of negative 6x squared. No worries there. What's derivative of negative 6x squared? Very good. Negative 12x. Minus 5 is a constant. Constants hold over. And then take derivative of e to the x. But that's the easiest thing in the world to take derivative of. What's derivative of e to the x? E to the x. There's my first derivative. I'm circling because that's my answer. And now let's take the second derivative. The derivative again. What's derivative of negative 12x? Negative 12 minus, what's derivative of 5 e to the x? Well, 5 is a constant, holds over. Derivative of e to the x is e to the x. And there's my second derivative. Does that make sense? Well, let's pick on it. But you know we're going to sit there and throw a bunch of product rule, chain rule, and quotient rules at you guys because that's what we do. So let's take a look at this next guy. Find a formula for g prime of x and determine the slope of the tangent line, or better yet, g prime of 2 if g of x is equal to, let's write that down, g of x is equal to 4e to the 5x cubed minus 9. So, I'm going to take my derivative. Well, pause, hesitate, read the problem. The function is 4e to the 5x cubed minus 9. 4 is a constant. Constants hold over. What's derivative of e to a function? Derivative of e to a function is e to the function times derivative of the exponent. So 4 holds over. Derivative of e to a function is going to be e to the 5x cubed minus 9 times, chain rule version of it, derivative of the exponent. What's derivative of 5x cubed minus 9? Well, derivative of 5x cubed is going to be what? 15x squared, and derivative of minus 9 is 0. And traditionally, if I was going to put this one on a multiple choice kind of a test here, I would put my two constants and multiply my stuff together just to make it look good. So, what is 4 times 15? 60. X squared, go ahead and put that term out front, just combining my like terms, times e to the 5x cubed minus 9. Does that make sense? Well, the 1, there's the answer. And now they ask you, and they're trying to give you this, remind you of the stuff we did before. If I ever ask you, find the slope of the tangent line, what are you supposed to do? Find the slope of the tangent line at x equals 2. What am I going to do? Plug 2 into the derivative, and that's really what they're asking when they're asking for this slope. Find g prime of 2. So g prime of 2 would be equal to 60 times 2 squared times e to the 5 times 2 cubed minus 9. At this point, it's nothing but a bunch of number crunching. 2 squared is 4. And 4 times that 60, just go ahead and clean them up, is 240. E to the 2 cubed is 8 times 5 is 40. And 40 minus 9 is how much? 31. And you leave them like that, because if you stick them in your calculator, e to the 31 is kind of huge, and you're going to go scientific notation. Just to show you guys, the 240 e to the 31 is, 6.97 e15 over there. That's times 10 to the 15th. It is a very large number. Does that make sense? So typically, if they ask you this on Hawks, type it in like 240 e to the 31. Does that make sense? Questions? All right, look at the next one. That's going to ask you this. The population of an unknown bacteria in an experimental culture is estimated by the population function n of t equals 10,900 divided by 1 plus 49 e to the negative 0.1 x, where x is the number of hours after the experiment begins. How fast is the population changing at the end of 3 hours? Round your answer off to the nearest integer. All right, so again, back to word problems again. So it's the same kind of word problems you guys had before, except we just got new functions now. Logs and exponents and stuff. So, here we go. How fast is the population changing? How fast is a fancy word for rate. And when you imply rate, what you're going to be doing? Take derivative. So this is kind of code in terms of word problems here. So there's a couple of different ways you can do this. Look at your function. N of x is equal to 10,900 divided by 1 plus 49e to the negative 0.1x. Now, there's two ways I can do this. I can clean this guy up, or I can take derivative of it the way it looks. If I take derivative the way it looks, because that big old division right down the middle, I would have to use the quotient rule. Derivative the top times the bottom minus the top times derivative the bottom all the bottom squared. That's fine, but there's going to be a trick to it because the top is a constant. So when I take derivative of the top, you end up getting 0. So a lot of stuff cancels out here. The other way I could have done this is clean them up. I don't like stuff on the bottom, especially when I have a constant on top. So I can take the thing on the bottom, but I bring it to the top, but I got to make the entire exponent of the guy negative. Which way would you like me to do it? Bring it to the top. All right, I'll do that. So bringing it to the top, that 10,900 is a constant, times 1 plus 49 e to the negative 0.1x, close parentheses, raised to the negative 1. Does that make sense? I just brought him to the top, but parentheses around the whole thing and make the exponent negative. And this is implied to have a power of 1 on it. So now I'm going to take my derivative. N prime of x would be equal to, now 10,900 is a constant. You're taking derivative of this 1 plus 49 e to the negative 0.1x raised to the negative 1. This is a chain rule. Function on the inside, that negative 1 power on the outside. Chain rule. Derivative the outside, inside stays the same, time derivative the inside. So the negative 1 pops down here and multiplied times the 10,900. That gives you negative 10,900. The inside, 1 plus 49e to the negative 0.1x stays the same. Raised to the subtract 1. Minus 1 is minus 2 times the derivative of the inside. This is for your benefit. What's the derivative of 1? 0. Plus 49 is a constant that holds over. What's the derivative of e to a function? Anything other than e to the x, you've got to use the chain rule, e to the function. Derivative of e to a function is e to the function times derivative of the exponent. So derivative of e to the negative 0.1x is going to be e to the negative 0.1x times derivative of the exponent. Let's do negative 0.1x times negative 0.1. Derivative of a constant times x is just a constant. Okay? Now, there's my answer. But of course, I'm going to clean this thing up. Now, plus, that 0 was for your benefit, so I don't need to write that. So I'm going to multiply my constants. What is negative 10,900 times that 49 times that negative 0.1? So make sure you show you on the calculator here what this is. Negative 10,900 times 49 times negative 0.1 is 53,410. So n prime of x is equal to 53,410, putting my constants together, times e to the negative 0.1x. But where does the negative exponent go? Where does this term, 1 plus 49 e to the negative 0.1x raised to the negative 2? Well, negative exponent makes them go on the bottom, that negative 2, so I'm going to bring them down here. That'll be divided by 1 plus 49e to the negative 0.1x squared. And take the negative exponent on the top, bring them to the bottom, make them positive. There is my derivative function cleaned up. Oh yeah, what was the question here? Oh yeah, the question is, how fast is the population changing? So we took a derivative at the end of 3 hours. What are we going to do? Plug in 3. So n prime of 3 would be equal to 53,410 e to the negative 0.1 times 3 divided by 1 plus 49 e to the negative 0.1 times 3 squared. Now, I want everybody to pay attention because I've seen a lot of folks make some mistakes. Not just on your last test, bonehead, careless here. Things like this. This is the kind of stuff that folks are making mistakes on. And so let me grab another nice little clean sheet of paper here. Here's one. This is why I wanted to do this on the calculator with you guys. I saw on your last test, I made you guys plug in a bunch of negative numbers into a function. And it was something like this. Negative 2 squared. What's negative 2 squared? Do you know how many people in here put -4? Because I'll put it on the calculator, Dr. Taylor. Yeah, you sure did. This is what you did. You did -2 squared. And it's -4. The calculator lied to me. No, you lied to the calculator. What does this thing have around it? Parentheses. Order of operations. What's your order of operations? You always do one inside parentheses first, then comes exponents, then comes multiplication, division from left to right, then addition, subtraction from left to right. Your classic order of operations. And because there's no parentheses here, it's going to do no parentheses, exponent first. And as you see the 2, it's only being squared. Then you negate it. That's why it's -4. But that's not what we got. We got -2. -2 squared. And what's -2 squared? That's actually the real answer. When you square a negative, negative times negative is positive. The answer is really +4. But stuff like this is messing people up because they're just mindlessly putting on their calculator and they're not thinking about, hey, I have a negative number plugged in. I need parentheses around this thing when you power that kind of stuff up. So, all right, so that's just kind of a point I want to show you. So I'm going to type this in and show you guys what's going on. And this, I'm using my calculator on this one. So it's a big fraction. So parentheses are in your numerator. 53,410 e raised to the -0.1 times 3. And all that's in the exponent, then over arrow, close parentheses. That's actually my numerator, but I got to put parentheses around my numerator, divided by parentheses around your denominator. It is 1 plus 49 e raised to that -0.1 times 3. And then I got over a close parentheses for that, and then that denominator is being squared. Does that make sense? And when I get this, what do I get? I got 28.439000571. The last thing is there's a Hawks problem waiting for you guys just like this one, and if you don't listen and read directions, you're going to get it wrong even though you got the right answer up there because you didn't give it to them the way they wanted it. How do they want it? Round it to the nearest integer. So n prime of 3 is equal to what? What would be your nearest integer? Well, that's 28.4, but anything less than 0.5, you round or drop it off. Anything 0.5 or bigger, you round up. So what's my answer? 28 what? It's a word problem, therefore I expect units. What's my units? Okay, it's a rate. So the function n is bacteria. You got that right, bacteria, but it's a derivative, which means it's a per. Very, very good. Bacteria per time is measured in hours. Bacteria per hour. 28 bacteria per hour is what this thing's growing at after 3 hours. Does that make sense? Did I lose you guys anywhere? All right, take a look at this next guy. Yep, same questions that I put on your last test, just different functions. Determine the intervals of which f of x equals e to the 2x minus 4 quantity squared is increasing or decreasing. They want intervals of increasing and decreasing on this guy. For intervals of increasing decrease, I want a first derivative number line. Intervals of concavity, I want a second derivative number line. See last test. There it is. So, first thing I'm going to do is take my function and take derivative of it. This increase decrease is a first derivative number line. So f of x is equal to e to the 2x minus 4 squared. So to take the derivative of this guy, what you got here, listen to my words and don't be panicky about this stuff. It's chain rule within chain rule. You see that squared on the outside? That's chain rule. Chain rule. Take derivative of the outside, inside stays same time derivative of the inside. But when you take derivative of the inside, that's not just e to the x, that's e to the 2x. Anything other than an x, you're going to use the chain rule version of the e. So you've got a chain rule within a chain rule. But don't worry, just follow your words. Chain rule. Take derivative of the outside. That 2 pops out front. The inside, e to the 2x stays the same, minus 4. Raised to the first power, derivative of the outside, inside stays the same. Times derivative of the inside. Derivative of e to the 2x. Derivative of e to x is e to the x, but e to a function is e to the function times derivative of the exponent. So derivative of e to the 2x is e to the 2x times derivative of the exponent is 2. And derivative minus 4, being a constant, is 0, so that goes away. This is my answer. So, I'm going to clean this up. F prime of x is equal to 2 times 2 is 4 times e to the 2x times the e to the 2x minus 4. Anything to the first power is himself. So this is my derivative. But we want to find intervals of increasing and decrease. I'm going to draw myself a number line and label it with the derivative. But what do I put on my number line? I got to put my critical numbers on there. How do you find critical numbers? You take that first derivative and do what with it? Set him equal to 0 and solve. Now I'm going to do this only once and then remind you the next time after that. All right, then you set each factor. See, it was already factored for you. After you set a function equal to 0, you factor it and you set each factor equal to 0. Well, 4 e to the 2x, I'm going to set that factor equal to 0. And the other one is e to the 2x minus 4. I'm going to set that factor equal to 0. How would you solve this guy? I want to remind you of this because it's very important. How do I solve 4 e to the 2x equals 0? What's my first move? Before I do log, before I can take that log, I got to get e by himself. All right, so let me explain to you guys because you guys are cool and hip to understand this. You see this e dude right here? You want to kill him off. How are you going to kill somebody? You got to get him by himself. Think about it. Okay. This kind of, I mean, I make up this stuff, but this is the stuff people remember. It's so sad. All the great math I teach, you remember the things I come up to try to connect you guys. So if I got to kill this dude off, I got to get him by himself first. Isolate your victim, right? So what's your first move? Get rid of the 4. Divide by both sides. Does that make sense? So first thing you're going to do is divide by 4. Get the e by himself. Now, and 0 divided by 4 is 0. Now, what kills off e's? What's the inverse of the e? What you can do? Now you take the natural log, but you got to get the e by himself first. So now take the natural log of both sides. And what is the natural log of 0? Oh, it's 0? Oh, no, I want you to actually put it on your calculator because I want everybody to see this. You're taking natural log of both sides. Natural log is 0, nothing but a number. What is it? Natural log of 0 is 1. No, that's not what I got. I got error message. Why is it an error message? You're supposed to remember this. The domain of log, you can only take the logs of positive numbers. You can't take a log of 0, nor can you take the log of negative. So what do you get here? Does not exist. What I'm trying to tell you is this, and then divide by 2, who cares? There's no solution for this one. E to anything never equals 0 because you can't take, you got to get rid of the e, you got to take log of 0 and it doesn't happen. So just, it's a nice thing to remember when I got, e to the something or other equals 0, just blow that off because e will never be equal to 0. You can't solve for it. So, because it's always positive when you throw in exponents into an e. So no solution on this one, but this one's different. Solve for x here. So I got e to the 2x minus 4 equals 0. I'm going to add 4 to both sides to get that e by himself. E to the 2x equals 4. Now, what kills off that e? Natural log. So this cancels, so you get 2x is equal to the natural log of 4. You with me? And now, what you got to do to solve for x? Divide by 2. And it's an awful number. X is equal to the natural log of 4 divided by 2. And for those people that just want to know, the natural log of 4 is positive, so it's not to go. Then you close the parentheses there and divide it by 2. It is 0.693147, whatever. Okay? But I'm going to use natural log of 4 divided by 2. I'm going to use its cleaned up version of the answer. So that's the only number I get to put on my, that's my critical value there. So I'm going to put that number, natural log of 4 divided by 2. There's my critical number. And notice it's divided by a number line into 2 spots. So now I'm going to pick a test value in each interval. So remember, this is about 0.69. So pick a number less than 0.69. Use your brain. Good choice. 0. And I'm going to plug 0 into my function. This would be 4 times e to the 2 times 0 times e to the 2 times 0 minus 4. I'm just trying to get you guys to do some math in your head here. Don't rely so much on the calculator. 2 times 0 is 0. And what's e to the 0? What's anything to the 0 power? 1. So this is 1. E to the 0 is 1. So you get 4 times 1 times 1 minus 4, which is negative 3. The answer is actually negative 12. But just wanted to work the numbers with you. But you don't really care about the number. What sign is it? It's negative. That tells me on first derivative, that's decreasing. Now pick a number bigger than natural log of 4 over 2. bigger than 0.69, I choose 1. All right, but this one, 1's not going to be very nice to plug in. So I'm going to be 4 times e to the 2 times 1 times e to the 2 times 1 minus 4. And I am going to stick that one in the calculator because e squared is not a really known number here. 4 times e squared, 2 times 1 is 2, over error times e squared minus 4. And decimal crappy number, it's 100 and point something or other, 100.1677, whatever. Don't care what the number is. What's the sign of it? It's positive. Everybody in here is positive. So to answer the question, very simply, you have this. Intervals of increase and decrease. So it is increasing on the interval between parentheses around, always open parentheses around your critical numbers. The natural log of 4 divided by 2, comma, to infinity. That's where it's increasing at. And it is decreasing on the interval between negative infinity to that natural log of 4 divided by 2. And this is the way you would literally put it into your Hawk system. And use that natural log of 4 with the fraction divided 2 number in there. Does that make sense, though? And also remember, when you're setting these functions equal to 0, e to whatever something with x in it equal to 0, it never happens. No solution on that part, and you can just go ahead and mark it off. Section 5.5. Section 5.5 is on exponential functions of growth and decay. And so, jump in with both feet, but there's going to be some formulas that you guys need to know here. All right, it says this. A quantity that increases at a rate of change that is proportional to the amount present is said to be, it's said to increase exponentially. Increase, okay, it's going to be going up, but the key word here is that word exponential. And this is where that e shows up. And I talked to you guys about anything that grows at a rate proportional to itself, that's that e to the x look to it. And that's why that e, 2.71828 number, shows up in nature naturally. So they're setting you guys up. So, exponentially. In a compound interest formula, a equals p e to the rt, the old PERT, r is called the constant. Okay. R is called the constant of proportionality. It's also known as the interest rate, but it's the constant of proportionality. And it is the interest rate. A function y equals f of t satisfies the equation dy over dt equals ky if and only if y equals c e to the kt. It's the same formula, we're just changing letters on you. So we just want to let you guys know what we're doing here. So this dy over dt is called a differential equation. Because you got a derivative equal to the actual function. Dy over dt equals k times y. When you actually solve this differential equation, your solution is always going to be y equals c, some arbitrary constant, e to that proportion k right there in front goes actually in the exponent k times t. Okay? And k and c are positive. We say that y grows exponentially. When the c and the k are going to be positive constants there, then y is going to grow, y grows exponentially. If a quantity declines at a rate proportional to the amount, the quantity is said to, instead of increase, it's going to decrease or decline, if you will, exponentially. So just as easily as you go up, you can go down. But if you're going down, it's called it declines or decreases exponentially. And what's the difference? Here's the difference. The function that models the quantity that decays exponentially is y equals c e to the negative kt. It's the same formula except for one thing. That k, instead of being positive, is going to be negative in that exponent. When it's negative, it's called an exponential decay or declines. When it's positive, it's called a growth model. It's the same formula. This is a growth, this one's a decay. K being positive versus k being negative. Okay? And then one more here. The model of the mathematical model for a limited growth is, here's one more formula. You know to use this formula when it says limited growth. This would be y is equal to some arbitrary constant times 1 minus e to the negative kt. This is your limited growth model. Okay? Y equals c times 1 minus e to the kt. So it's got this thing here. With the limited growth, the biggest this thing's ever going to get is going to be c, where c and k are positive constants and stuff. All right? However, when you start working in the world of decay, exponential decay, you are going to work in the world of basically radioactive, and they talk about things like half-life and stuff like that. And here it is. The amount of time required for a half the material to decay is called the half-life of the material. You know, so when you're looking at something like, even in science, carbon-14 dating, this is how they try to figure out how old a particular object is. They analyze the carbon-14, not just the kind of standard carbon, which is carbon-12. They look at the radioactive carbon, called carbon-14, and then they analyze that fine fact to see how much is in there compared to when it was new, how much should have been in there, and that decay helps to model how old something is, okay? And they typically use with carbon-14, there's a half-life, how long it takes for half the carbon-14 of a subject to be able to cut in half, and they kind of use that to figure out the age of certain objects. Now, we've got some more formulas here. Now, so, here's your other formulas. Let me grab a nice little sheet of paper over here and just talk about these guys. Now, we talked about a few seconds ago, we have this. Y equals e to the x. What's derivative? E to the x. It's the only function in the universe, it's its own derivative. But what if you got y equals a to the x? A different base. A base has to be positive, but you're studying something or other, and you don't have that famous magic e, 2.718. You got something like 3 to the x or 17 to the x. You got a different base. It's still an exponential function, so there's a pattern. And the pattern is the derivative of a to the x, again, a is a different base than e, is still going to be a to the x, but since you did not have that e, you have to have an adjusting factor. And your adjusting factor is times the natural log of a. So the derivative of a to the x is going to be a, not being e, is going to be natural log of a times a to the x. You still get that a to the x back again, but you got this constant adjusting factor for not having e in the problem. And because for every rule you got the rule, then you got the chain rule version of it. The chain rule version of this rule is this. If y equals a raised to some kind of a function, then y prime is going to be the natural log of a times a raised to that function, but the chain rule version, you got to do times the derivative of the exponent, times f prime of x. So 2 more rules. So what are we up to? Rule number 5 and rule number 6. Exponentials, but when you don't have that magic number a. Okay? So you got 2 to the x or 17 to the x. You can still take derivative of it. Derivative of 17 to the x is going to be 17 to the x times the natural log of 17. You got to put that adjusting constant with it. Okay? So, and that's what they're talking about here. So, if f of x equals, instead of using a, they use b to the x, then f prime of x is going to be equal to the natural log of b times f of x. They write it like this because they're trying to show you this differential equation, but f of x is b to the x, so they really get what I just gave you. You get the natural log of b times b to the x. That's really the rule. The derivative of b to the x is going to be that adjusting factor, natural log of b times b to the x. And then you got the chain rule version of this guy. If you got f of x is equal to b raised to a function, then the derivative is going to be the natural log of b times that b raised to the function. Within chain rule, you got to do times the derivative of the exponent. And two more little formulas here as I'm sliding this thing up. If you got y equals the natural log of x, what's derivative? What's derivative of natural log of x? We've got that memorized, chapter 5.3. What is it? 1 over x. Very good. Okay? Things you have memorized. Y equals natural log of x, then y prime equals 1 over x. But what if we don't have a natural log? Natural log is log base e. What if we got something like y equals the log base a of x? What's the derivative going to be? Well, it's still a log, and derivative of a log is 1 over. So derivative of log base a of x is going to be 1 over x, but because you don't have the natural log, with that base e on it, you got to do an adjusting factor. And the adjusting factor is times 1 over the natural log of that base a. So when you do the exponents, you multiply times natural log of a. When you do the log, take derivative of that, you got to do times 1 over the natural log of that base a. Logs, the natural log of base a shows up in the denominator. With exponentials, the natural log of a shows up times the function in the numerator. Does that make sense? And then you got, so this is rule number 7. And rule number 8, if you got y equals the log base a of a function, then y prime is going to be, because you don't have natural log, you got to do 1 over the natural log of a for the adjusting factor times 1 over the function times the derivative of the inside chain rule version of this guy. So every rule, there's the rule, and then there's the chain rule version of that rule. So that being said, they wrote it up with the log base b, so we get to write this thing up again. It says this: if y equals the log base b of x, then y prime is going to be 1 over the natural log of the base on this one is b times that 1 over x. Derivative of a log is always 1 over. That 1 over is what I'm trying to drum home to you guys. So if you got the log base b of x, it can be 1 over natural log of b times that 1 over x. And if you got y equals the log base b of a function, g of x, it's going to be 1 over the natural log of b for that adjusting factor, times 1 over the function, which is g of x, chain rule, times g prime of x. Does that make sense? So there's a rule and there's a chain rule version of it. But the nice thing about it is you just have to multiply. It's just like before, except an adjusting factor. Exponentials, you multiply by natural log of whatever the original base was. And with logs, you multiply by 1 over the natural log of whatever the base on the log is. So here we go. Let's look at some of these problems here. Here's the one example from your video example. So please go back and watch your Hawks TV and look at those examples that they do here. It says this: a population of wolves grows exponentially at a rate of 5.5% per year. The population was 7,100 in 2008. Find the exponential function that represents the population t years after 2008. All right. When you see something grows exponentially, we have this formula that looks like this. It's y equals, you can use either p e to the kt, because if that grows exponentially is that same style PERT formula that we used before, or you could use the formula y equals c e to the kt. It's your choice on which model you want to use, because if you look at them, they're both the same thing. And that r and that k represents the percentage. So if I use this guy, the k, the r, which is your k, 5.5%, that's great, but remember, percentage are for people who can't do math. What's 5.5% also known as? 0.055. And p is the same as your initial amount, which is C. And what is the initial amount of wolves? Initial amount was 7,100. Okay, so you get this equation, and time is going to be, and this is what you're measuring, time is going to be years, and we're measuring it since our beginning, because that 7,100 was in 2008, years since 2008. So I get the equation, y is equal to 7,100 e to the 0.055 t. Does that make sense? This is your modeling equation. You can call him y if you want to. You can call him f of t because he's based upon the t variable. I got a question for you. What if it's not the case right now? We got a problem with wolves and with coyotes in North Carolina and stuff like that because they put those things into the community, and then they just started to grow, and then they're just growing all over the place, and now the hunters are having to have something else to shoot, so they're looking after the coyotes because they do tend to damage the cows and the goats and the whatever that's in your field and stuff like that, so they do tend to kill those things, so it's a real problem. So based upon that, what if they use the word, instead of exponentially grows, they exponentially decay? What would the difference be? You would make that percentage, that 5.5%, and that 0.055 make it negative. Other than that, it would be the same way. But making it negative would mean the population is decreasing. But because the population is increasing, your rate is going to be positive. Okay? Now, for part B, or number 2 here, what will the population be in the year 2018? Well, here's what you have to do here. Now, this thing was measured 2008. So that's when T started. 2008, T was equal to 0. So what do you think 2018, what is T going to be equal to? When T measured since 2008. So 2018 is how many years? How many years? 10 years. 2018 minus 2008 is 10 years. Does that make sense? So T equals 10. So my F of 10, which would be Y, is equal to 7,100 e to the 0.055 times 10. And again, let's make sure we don't screw this up. So I want to always show you guys how I put it in the calculator, but this is in the exponent. So make sure you leave it in the exponent. So it's 7,100 e raised to the 0.055 times 10 in the exponent. If you want to, you can always put insert and put parentheses, oops, wrong button there, parentheses around your exponent. Does that make sense? And how much do I have? I've got 12,306.09643. Does that make sense? So you're supposed to round it to the nearest what? Whole number, and that would be what? 12,306. Rounding to 3,006. What? Wolves. Go past. There it is. Okay. 12,306 wolves. Does that make sense? Now, number 3, last one on this one, it says this. In what year will the population be 21,330 wolves? So here's my equation again. The population, which is your F of t, we can call him y, is equal to 7,100 e to the 0.055 t. So the population in the future is, so this is going to be my y, 21,330. So I'm going to have 21,330 equals 7,100 e to the 0.055 t. What are you going to do to solve for t? What's your first move? The t is in the exponent of an e. You got to isolate your victim. How are you going to get him by himself? What's your first move? Divide by 7,100. So this cancels. And you're left with, if I put that on the calculator, 21,330 divided by 7,100 is, yep, it's a awful decimal. So I'm going to leave him just the way he is. Doesn't matter. So I'm going to get 21,330 over 7,100 is equal to e to the 0.055t. What's your next move? Now you got the e by himself. Now take the natural log of both sides, because the natural log and the e are going to cancel. That leaves you with the natural log of 21,330 over 7,100 is equal to 0.055t. What's your last move to get t by itself? Divide by 0.055. And then go put him on your calculator. And then we've got to answer the question. So here we go. It's the natural log of, parentheses, 21,330 divided by 7,100, close parentheses, divided by 0.055. And I get 20.0003590 what? Years. But again, read the question. In what year? When did we start measuring this stuff? So the year, you started in 2008. So the year would be 2008 plus pretty much 20 years. They want you to round it off to the nearest year, so I'm going to use just 20 years. So what does that give you? What year will it be? 2028 is what year that we're going to actually get our population. Does that make sense? Did I lose you guys anywhere? Study hard on this stuff. We will finish up the practice problems next time, and then we'll also talk about your homework set and get ready for your next test and moving on into chapter 6. So see you guys then.